In this video, we discuss some straightforward extensions of the overlapping generations model that lead to the prediction of a poverty trap. That means that in this framework, multiple equilibria will emerge, and one equilibrium will be associated with a low income level, out of which the economy cannot grow by itself. So it needs exogenous interventions from abroad, development assistance, to push this economy out of this low income equilibrium. The discussion is based on the papers by Azariadis, published in 1996, The Economics of Poverty Traps, Part 1, Complete Markets, in the Journal of Economic Growth, by a paper by Bloom and co-authors, Spurring Economic Growth Through Human Development, Research Results and Guidance for Policymakers, which is forthcoming in the Population Development Review, and a textbook treatment of various aspects that can lead to poverty traps can be found in chapter 21 of the book by Asimoglu, Introduction to Modern Economic Growth. So as I said, some simple modifications of the basic overlapping generations model can explain the emergence of poverty traps out of which a country cannot grow on its own. Now, the two simple extensions we make here are that we introduce subsistence consumption C bar in the first period of life. So individuals need a certain consumption level C bar, otherwise they do not survive into the second period of life. We conceptualize this that if the actual consumption level of a household would fall below the subsistence consumption level, then utility becomes minus infinity. Now, as long as households cannot afford their basic needs, they would not save. So we would not have capital accumulation in the model as long as incomes are not so high that at least the basic subsistence needs are covered. In order to make this a possible equilibrium in the model, of course, we need a situation where the production function is still positive, so output in the economy is positive, even without any capital input, because otherwise the economy would vanish, we wouldn't have any income at all. And we achieve this by introducing the production factor agricultural land, denoted by X, which is of fixed supply. And in this sense, an agricultural economy can produce output simply by using labor on land. So you have an agricultural economy where agricultural workers work on the given land without any capital. Now, the utility maximization of households has actually two solutions. One is an interior solution for optimal consumption when consumption is above subsistence, and the other one is a boundary solution when income is so low that households could not afford subsistence consumption. So we conceptualize the utility function in the sense that we have two situations. So if subsistence consumption needs in the first period can be fulfilled, then the utility level of the household is the logarithm of consumption over and above the subsistence need. So utility starts to increase once the basic needs are fulfilled. And we have discounted utility from the second period of life. And here we just, for simplicity, assume that in the second period of life there is no subsistence consumption. And this can be explained intuitively just by the fact that after the second period, individuals die anyway, so they do not need to live into the third period. But if subsistence needs cannot be covered by the given income level, then utility is minus infinity. The budget constraint is as in the basic model, so total income in the first period of life needs to cover consumption expenditure in the first period of life plus discounted consumption expenditure in the second period of life, and second period of life consumption is again discounted with the market interest rate, RT plus 1. Now we again write down the Lagrangian function, which is the utility function here, so the first part, plus the Lagrange multiplier times the budget constraint where we subtract from WT the right-hand side, CT minus CT plus 1 divided by 1 plus RT plus 1. And then we can compute the necessary first-order conditions in the situation that the subsistence needs can be fulfilled. Otherwise, we would be in the boundary solution where saving in the first period is 0 and total income is spent on consumption. Now, if we take the derivative of the Lagrangian with respect to consumption in the first period, Then we see that's the logarithm. So we have 1 over what we have in the logarithm here, ct minus c bar times the inner derivative, which is 1. And we have here minus ct, so we have minus lambda. And if we rewrite, we get this condition that 1 over c minus c bar is equal to lambda. And the second necessary first order condition is given by the derivative of the Lagrangian with respect to consumption at time t plus 1. So we have then here beta divided by ct plus 1, because that's the derivative of the logarithm of ct plus 1 with respect to ct plus 1. And here we have minus lambda divided by 1 plus rt. So if you bring it to the right hand side, it's positive. So these are the two necessary first order conditions with respect to the consumption choice. And of course, we also have the third variable, the Lagrange multiplier, and we have a third equation also, which is the budget constraint. So we can solve a system of 3 equations with the 2 necessary first order conditions plus the budget constraint to solve for the 3 unknowns: consumption in the first period, consumption in the second period, and the Lagrange multiplier. Given these necessary first order conditions, we can then compute consumption in the second period, ct plus 1, and in a corner solution that's 0 because people didn't survive into the second period basically. But in the interior solution, we would take lambda, plug it in here, so that we have in the denominator 1 plus rt plus 1 times ct minus c bar. We bring the beta to the right hand side, and then we just change numerator and denominator on the left hand side and on the right hand side, and then we would get this expression here. So consumption in the second period would again depend positively on the discount factor. That's intuitive. If people put more weight in the second period, so if they are more patient, they would ceteris paribus consume more in the second period. If the interest rate increases, the same holds true, because then people have more capital income to consume in the second period. And of course, if consumption is above the subsistence consumption level, then also second period consumption would increase, because that only allows people to save. So then we can plug the interior solution into the budget constraint, and from that we see that 1 plus rt plus 1 cancels out in the numerator and the denominator, and we can then multiply out beta with ct minus c bar, and we would get an expression where we would have related the wage rate at time t to consumption at time t, which is 1 plus beta times consumption at time t. But now, in contrast to the basic model, we have to subtract the term minus beta times c bar here. And as we will see in the next slide, basically this additional term makes the saving rate a non-linear function actually of income and also consumption. Now we can rearrange this expression here to isolate consumption in the first period. So we would bring the term beta times c bar to the left hand side. So we have wt plus beta times c bar, and then we divide by 1 plus beta. And this would lead to exactly this expression here, where consumption in period t is a positive function of wages. And we can, with a small trick, write this in the way that it is written here, where we basically put out wt from the first expression. In the second expression, we do not have wt, but if we multiply the numerator and the denominator by wt, then we can basically pull one wt out, and we have this expression here as the factor with which we multiply wages. Now, in this case, that's nothing else than 1 minus the saving rate at time t. Now, the saving rate depends on time because we have this expression here in the saving rate. The subsistence consumption level divided by the wage rate. So the saving rate is time dependent and will change over time. Particularly, it will change with the wage rate. And we will see that the saving rate becomes higher when the wage rate increases. So now we can again simplify things and compute the saving rate explicitly from this expression here. And here we exactly have the effect that I've said before. So the saving rate at time t now depends positively on the wage rate, because if the wage rate increases, the negative term here decreases, and wages would, the saving rate would increase in wages. The interpretation is that the saving rate is very low if the wage rate is rather low, and particularly when it is below the subsistence level, then we would have that the saving rate equals 0. So if the wages are very low, people cannot afford to save because they have to cover their subsistence needs. And only with a rising income level, so as the wages go to infinity, the saving rate would approach the saving rate of the basic model of overlapping generations. So poor households save only a little or nothing at all, while households with higher incomes have higher saving rates, and that's actually consistent with the stylized facts from an empirical point of view. So this model then captures the important empirical regularity that the saving rate increases with income. Poor households save only a little, higher income households save more. And for illustration, I've plotted here the saving rate for an increasing income level for the given parameters when beta is equal to 0.6 and subsistence consumption needs equal to 2. Now, if the wages are lower than 2, of course, the saving rate is 0 because then people would use all their income to buy consumption to be able to cover their subsistence needs. Only once income increases above the level where subsistence needs can be covered, the saving rate increases. It increases with a steeper rate at the beginning, and then this rate slows down and it converges in the long run to the level beta divided by 1 plus beta, the saving rate in the standard overlapping generations model. Now we have to close the model again, and to this end we again assume that the production side of the economy follows a Cobb-Douglas production function of the particular form that we have here, and the only difference to the basic overlapping generations model is now the presence of X, which is agricultural land that is constant and of fixed supply. So now output is produced with technology is constant and exogenous, capital, and land with an output elasticity of alpha, and labor with an output elasticity 1 minus alpha. Now the crucial point here is that if the capital stock is 0, so if K is 0 and does not exist, the economy can still produce output because there is land and labor, so workers would produce food basically on the available land. So for K equals 0, production can still be positive. And that's important because in the baseline overlapping generations model, we could not have an economy without capital, basically. Now, the wage rate is again the marginal product of the production factor labor. So to compute it, we take the derivative of output with respect to L. Then 1 minus alpha comes down from the exponent. This part here stays unchanged, and the exponent is reduced by 1 here. So this 1 cancels out. Now we see again, we can write L to the power of alpha in the denominator. So we would then have alpha here and alpha in the denominator of L here. So we can just put this together. So we have then capital per worker on the right hand side, the first term in parentheses, and land per worker as the second term here in parentheses. And capital per worker is lowercase k as before in the baseline version of the overlapping generations model. Next, we need to write down the capital accumulation equation. And in a basic form, we know capital per worker is given by gross investment. That's the same as in the basic version of the model, plus the capital per worker that is carried over from the previous period, minus depreciation of capital per worker. Now, however, the difference comes into play because we plug in the saving rate from the previous slides that we derived there, and we see the saving rate now is not the constant beta divided by 1 plus beta as it was in the basic version, but it also includes the term in parentheses that depends on the wage rate and therefore depends on time. Now we just multiply this out here, so the WT vanishes in the second term, and here we have WT. And so we see that WT, the wages, show up on the right-hand side of the capital accumulation equation, and we can substitute it out by the expression that we derived on the previous slide. So we plug this in and get an expression of the capital accumulation equation when wages are substituted out. Now overall, this is the capital accumulation equation if we have positive capital accumulation, but in the situation where nothing is saved, then capital in the next period would just be zero, or basically it could be the case that nothing is saved and nothing is invested, but the capital stock is still positive from the past, but then it will depreciate over time such that at some point it becomes zero. So overall, the capital stock at time t plus 1 is either given by this expression, or if the saving rate is zero and there is no capital anymore because everything has depreciated, then we would be in the corner solution with zero capital stock. Now we can again illustrate the model dynamics by means of a graph. We plot on the horizontal axis capital at time t, and on the vertical axis capital at time t plus 1. Again, for all steady state equilibria where capital at time t is equal to capital at time t plus 1, so where capital does not change over time anymore, it holds that they have to be along the 45-degree line, of course, because only there capital at time t is equal to capital at time t plus 1. Now, in contrast to the basic version of the overlapping generations model, we again draw the capital accumulation curve, but it does not start at the origin, because we have the possibility that we produce in the economy without any capital. So it could be that the capital stock is zero up here, and only then we have this concave function. So this function is again concave in the capital stock because alpha is smaller than 1. And again we have the situation that we subtract a linear term here because this factor here is smaller than 1. So this curve would flatten as capital increases. So the increase first would be steep, and then as capital increases, it would become flatter and flatter. So actually it would intersect the 45-degree line twice. So we would have an intersection here and an intersection here. And in addition, we would have another intersection basically when the capital stock is zero. And in this equilibrium, now the economy can still exist because it can produce agricultural output. It can produce food, and it could not have produced in the basic overlapping generations model. If the capital stock was zero there, the economy would have ceased to exist. Now what about the dynamics? We see 3 steady-state equilibria here. One with a capital stock of 0, one with a capital stock that is high, kt, and one in between, where this kt plus 1 line intersects the 45-degree line from below. Now what we will see is that this steady-state equilibrium is locally stable, and this steady-state equilibrium is locally stable, but the equilibrium in between is unstable. So it depends on whether we start to the right of this equilibrium or to the left of this equilibrium, whether we converge to the low capital equilibrium, that is also a low income equilibrium, because the capital stock is zero and there is only agricultural output, so this would be the agricultural economy. And when we start to the right of this unstable equilibrium, we would converge to the high capital equilibrium with high incomes that would be kind of a modern high income economy. We see this when we draw in the dynamics. So if we start with a certain capital stock, say K0, then we see that capital in the next period would be along the KT plus 1 line. So we would have K1 here. Then we draw K1 on the x-axis, so K increases step by step. K2 would then already be here, K2, so we would have K2 again closer to the steady state level, and we would converge to the steady state from below, to this steady state with a high capital stock basically. However, what happens now when we are to the left of this unstable equilibrium? In this situation, we see that actually if we start with this level of the capital stock, that capital decreases. So in the next period, we have a lower capital stock than K0. The capital stock would only be K2. So we would actually converge to a situation with a zero capital stock over time. And the zero capital stock then is the poverty trap equilibrium, where the economy does not have capital. It's an agricultural economy and people just produce food as an output. Now these two equilibria, or the basins of attraction of the two equilibria, are separated by this unstable equilibrium that is in between the two stable or locally stable equilibria. So here to the right we would have the basin of attraction of the high income equilibrium, and to the left of this red line we would have the basin of attraction of the poverty trap. And now the crucial point is that once we are here or in this equilibrium, the economy has no chance escaping this equilibrium on its own. So it cannot come into this basin of attraction without any exogenous push or exogenous intervention. And that's the theoretical explanation or justification for development assistance. Because in this situation, we could have that the richer countries coordinate and make a transfer of capital to the poor countries that push them so far outside that they get into the basin of attraction of their high capital stock and high income equilibrium. So the goal would then be for development assistance to push these economies so far out of their equilibrium that they end up with a capital stock that is in the basin of attraction of the high income equilibrium. So that's basically just a repetition of what I said. So there are two stable equilibria and one interior equilibrium that is unstable. And the economy only converges to the good equilibrium, quote unquote, if it has a sufficiently high initial capital stock. Otherwise, it converges to the bad equilibrium. And in this bad equilibrium, that's the poverty trap. Total income is consumed, capital would never accumulate, and the countries have no chance to grow out of this bad equilibrium on their own. So in this case, an exogenous shock is needed, and that is according to this big push hypothesis that a country needs a big exogenous push to be able to converge to the equilibrium that is associated with higher income. So to summarize, poverty traps are a theoretical foundation for development assistance. Sufficiently high transfers are needed in this kind of development assistance, but there could also be other aspects that push the economy into the basin of attraction of the high income equilibrium. In our case, we disregarded technology because it was exogenously given and constant, but in reality, technology transfers might also play an important role because if technologies are transferred from rich countries to poor countries, that might raise incomes there sufficiently such that they come into the basin of attraction of their high income equilibrium. But there are many, many other aspects and mechanisms that remain unconsidered here. And there are a lot of mechanisms of how one could generate poverty traps in an overlapping generations model, and many of them are described in the article by Azariadis that I've mentioned at the beginning, or in the book by Asimoglu in chapter 21.